Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska, Fairbanks. Welcome to Unit 12, the Planetary or Global Circulation. In this first slide, we start by reviewing the winds in Honolulu, Hawaii. We show two wind roses that summarize the strength and direction of the winds in Honolulu in January on the left and July on the right. A wind rose is a diagram where the petals of the rose point in the direction the wind comes from, and the length of the petal represents the fraction of time the wind comes from that direction. The petals are color-coded to indicate the fraction of time that the wind has a given strength. Green represents the strongest winds, with wind speeds up to 25 miles an hour or 40 kilometers an hour. The colors progress from green through blue, red, and yellow to black, which represents the weakest winds. We see that in both January and July, the wind roses show that prevailing winds come from the northeast and east-northeast. This pattern is most pronounced in July, with the east-northeasterly and northeasterly winds present over 80% of the time. Why do the winds in Honolulu behave in this way, and primarily come from one direction all year round? The prevailing winds in Honolulu highlight the question of this unit. Is there a systematic pattern to the winds on Earth? Wind roses from several sites in Alaska are presented in Chapter 5 of the Climate of Alaska. For many locations in Alaska, the winds are primarily northerly for most of the year, except in summer, when they are southerly. On the Arctic coast, the winds are primarily easterly in winter, aligned with the easterly current in the Beaufort Sea, and are driven by a semi-permanent high-pressure system to the north. In this unit, we look at how air moves or circulates on a planetary scale and determines the weather and climate of regions around the world.
The overarching question that we're looking at in this unit is what are the principal features of the global circulation and how does that circulation shape the weather and climate? And so the specific questions you can read here just to comment on them a little bit. Why are there dominant patterns to the weather? And is there some pattern underlying this dominant pattern that can be explained by general physics, that there's a primary forcing of the circulation of the Earth and then all the details are laid on top of it? We can come up with an ideal circulation based on our understanding of pressure and wind from earlier in the course, and we'll do that, and then we'll talk about how well this ideal circulation or model circulation matches the real circulation, and it's remarkably good. Up to about, I would say, 80% you can explain the large-scale circulation of the atmosphere with the concepts we have from this semester in class. The changing of that pattern with season, which is critical for agriculture, whether we have rainy spells or dry spells in different seasons. We also come back to looking at weather aloft, the jet streams aloft and how they control weather at the surface and how they fit into the general circulation. And finally, we look at the question of whether weather in different parts of the world is connected. When we have one kind of winter in Alaska, can we talk about having a certain kind of winter in the lower 48? Is there some connection across continents, between different continents, when we see one weather pattern in one region and another weather pattern in the other? This is called teleconnections, connections at a distance. So we begin with looking at a simple circulation that we might expect on Earth from the idea that the sun heats the Earth more at the equator than at the poles, so that the tropical regions are warmer than the polar regions. And therefore, we expect that as we heat the tropical regions, the air rises. Then if we think about our pressure gradient forces and how that gets set up between a warm column of air and a cold column of air, that air is pushed towards the poles by the pressure gradient force, sinks at the poles, and returns to the equator. There are two sets of pressure to think about here. The pressure aloft, there will be higher pressure aloft over the tropics than at the pole, and that's what pushes the air from the tropics to the pole. But at the surface, the sinking air, the falling air, causes high pressure, and at the surface, the rising air causes low pressure. So the surface pattern is that we have a high pressure at the poles and a low pressure at the equator. It's the same mix of pressure at the surface and aloft that we see in sea and land breeze locally. It's the same mechanism. This single cell circulation was first described by Hadley to suggest why the winds might be from the pole towards the equator in a overall circulation pattern of the Earth. In this simple model, we haven't taken into account rotation of the Earth. If you want, this is just a fixed Earth with no geography, and explains a global pattern of wind. It's also consistent with the pattern we expect from thermodynamics, that warm air is being carried towards the pole, carrying its heat with it from high temperature region to a low temperature region, following the laws of thermodynamics. When we look at the circulation on Earth that we actually get, we get a 3-cell circulation. The Hadley cell does not extend all the way to the pole, but the air travels to about 30 degrees north and south and then begins to sink at those latitudes. And so the Hadley cell is a tropical cell extending from the equator to the subtropics. If we look at that cell for a minute, we get low pressure at the equator in the rising side of the cell, high pressure in the falling side of the cell. We get cloudy weather in the rising side at low pressure. We get clear skies at the high pressure at 30 degrees north and south. The rising side of the cell gives us the great thunderstorms. The air is very warm and moist. We get deep convection because we're getting a lot of latent heat release from the water vapor in the air. And so we get the intertropical convergence zone marked by clouds, where the winds from both Hadley cells in the northern and southern hemisphere come together and rise over the equator. The falling air at 30 degrees north and south gives us clear skies and gives us the great desert regions that we see in both hemispheres. The surface winds in these regions are shown as the orange arrows. So in the northern hemisphere in the Hadley cell, the return winds at the surface are coming from the subtropics back to the equator. They are deflected to the right in the northern hemisphere and they become northeasterly winds, the northeasterly trade winds that carried people from Europe to the Caribbean. In the southern hemisphere, those winds are deflected to the left and they become the southeasterly trade winds out of the southeast. Aloft, the winds are heading away from the equator, and aloft the winds are westerly in both hemispheres because they're deflected to the right in the northern hemisphere and the left in the southern hemisphere, giving us westerly winds aloft. The sinking air at 30 degrees north travels both equatorward and poleward. The poleward air sets up a ferrule cell. This is a rather weak cell. It's hard to find in the atmosphere, but it fits the 3-cell circulation pattern. And so we get a cell called the ferrule cell where air is running from the warm to the colder regions along the surface. So we get winds traveling northward along the surface and then returning in the cell. It's a thermally indirect cell because the air is moving opposite to what we would expect from direct heating as it is in the Hadley cell. And then finally, the last cell that we get is the polar cell, which is a thermally direct cell. The cold air is sinking at the pole, warmer air is rising at 60 degrees north and south. And so we have a cell where the winds are coming from a high pressure at the pole outward to low pressure at 60 degrees north. The junction where the ferrule cell and polar cell meet, we have two air masses coming together. The density and temperature differences at that front, the polar front, are very pronounced because we have air that is coming on the polar side from the heart of the pole, the coldest region on Earth. We have air south of the polar front coming up from the subtropics, and so we get a very well-defined polar front, a cold front, and we get strong weather at the front as we would expect. We get major storms, and this is why we have the storm systems of the Aleutians, the storm systems of the North Atlantic, and the storm systems of the Antarctic Ocean, because we have this huge contrast that occurs at 60 degrees north and south. And so in the polar region, the pattern is wind coming out of the poles towards the equator. It is deflected to the right in the northern hemisphere, and those become northeasterly winds. In the southern hemisphere, they become southeasterly winds because they're being deflected to the left. At mid-latitudes, we have predominant winds that are westerly in the northern hemisphere because they're winds coming from the south to the north being deflected to the right by the Coriolis force, and they become southwesterly winds. Those are the predominant winds of Europe and southern Alaska and the Aleutians. So we see that our simple water world model with 3 cells gives us a pretty good explanation of the basic weather and climate patterns on Earth. If we turn to the observed circulation and look at the average patterns that we expect in January in the upper plot and in July in the lower plot, we do see a pattern of lows and highs with latitude. It's not as perfectly symmetric as we expect on our water world because the differential heating of the continents and the oceans sets up different variations. But we see high pressure systems at about 30 degrees north and south, a band of them around the Earth. In January, we also see a pronounced high pressure system over Siberia, and this is an example of a radiative high where we get intense cooling and sinking of air, giving us high pressure, giving us clear skies, which allows more cooling to occur. We get examples of this also over Alaska and Canada. They don't show up in the average of this map, but they are there. But the textbook example is the example over Siberia and northern China. We also get low pressure systems over the continents in the summer hemisphere because we get thermal lows where we get, due to heating, rising air over the landmass and therefore low pressure being set up at the surface. And so we get a pattern of the global circulation in the three-cell system and then an overlay of radiative highs and thermal lows sitting on top of that. But the basic pattern that comes out of the three-cell pattern does explain about 70 to 80% of what's happening on the Earth. For Alaskan interest, I'd highlight the pattern of the low pressure systems over Alaska in the winter in January, the Aleutian low, and that gives way to the northward motion of the Pacific high in July moving north in the Pacific, and that pattern is the pattern that dominates the weather in Alaska from summer to winter, this movement of the pattern with the seasons that affects local weather. Just to highlight those changes in terms of precipitation around the world, on the left we see the precipitation in millimeters, 200 millimeters, about 8 inches, with the rain in India. This is the monsoon rains that are critical every year for driving agricultural production in India and keeping nearly 1 billion people alive. That pattern of rain in India that occurs every year, if I can flip back to the previous slide, is to do with the fact that in the winter we have a high pressure system over Asia that sends air out from Asia, which is dry, and that's replaced by a thermal low pressure system over the Middle East forming in the summer that draws air in, so that in the summer air is being drawn up from the south over India and is full of moisture from the ocean and gives us the monsoons. A large part of what happens in the monsoons is that the air has to rise up over the Himalayas. Remember, the highest mountains on Earth are there at the north of India, and so India is steadily rising as you travel from south to north across India, and therefore we will expect more precipitation, and this is what happens in the monsoon pattern. Another example is in California. The Pacific high pressure system moves down over San Diego in the summer, giving clear skies and low precipitation. That's the panel in the upper right. And then an example of a thermal low pressure system in North America is in Tucson, Arizona, where in the summer you get a thermal low pressure system giving us precipitation in late summer in Arizona, New Mexico, and northern Mexico, called the American monsoon, if you will, the rains in late summer due to a thermal low forming. This behavior in the southwestern United States that we see in the lower right panel is also associated with the formation of the continental tropical air mass that you saw in your discussion of air masses. The formation of that air mass in summer is associated with the creation of this low pressure and rain that you see in the American Southwest. We've seen how weather at the surface is related to the structure of the winds aloft. The reason for such intense storms at 60 degrees north is because of the formation of an intense jet stream between the polar air masses and the mid-latitude air masses. As we discussed earlier, in the upper right panel, we have the Hadley cell, thermally direct cell. We have a Ferrel cell, which is not quite as well defined because it's thermally indirect, and then we have a polar cell from 90 to 60 degrees. If we look at the structure of the atmosphere in terms of air masses, we have a very abrupt change in temperature in a short distance where the mid-latitude and polar air masses come together. And so we get a very strong pressure gradient, and therefore we get a geostrophic wind with very high winds in a region that is pretty narrow in terms of latitude. The pressure gradient can be seen, if you will, by following the 500 millibar surfaces that fall dramatically across this front. And so this is why we get such intense storms at 60 degrees north and south, because they are supported by the presence of a very well-defined jet stream. There is also a jet stream at the junction between the Hadley cell and the Ferrel cell, the subtropical jet, but the contrast in the temperatures is not as extreme, and therefore the contrast in the densities is not as extreme. The pressure gradients aren't as extreme, and as a result the subtropical jet is not as pronounced as the polar jet, and it's the polar jet that we call the jet stream because it is the dominant jet. We've seen this already this semester, but just to repeat the idea that the jet stream doesn't flow perfectly east-west but meanders north-south, creating ridges and troughs and creating a wave structure. And that's how meteorologists talk about the jet stream in terms of waves, whether there's a large amplitude wave with high ridges and low troughs, if you will, or whether there's low amplitude waves with shallow ridges and shallow troughs. But the point is, as the air flows from ridges to troughs, there's convergence and divergence as the wind slows and speeds up, and this is tied to the ideas of vorticity that we've already looked at this semester, that we're on a rotating planet, and as wind moves north and south it changes its rotation relative to the Earth, and this is all tied together in convergence and divergence aloft. Convergence aloft, air coming together aloft, means that it flows downward and diverges at the surface, so convergence aloft associated with high pressure systems. Divergence aloft associated with rising air, and convergence at the surface and low pressure systems. And so the jet stream acts to support the storms at the surface. If the jet stream allows for strong divergence aloft, then it will allow low pressure systems to intensify at the surface, and this is part of the dynamics of storm systems and the idea of storm tracks, that storms, if you will, at the surface are pulled as if there's a puppeteer above with strings leading them from west to east around the globe as they follow the jet stream aloft. The atmospheric circulation and the ocean circulation are tied together because as the winds blow over the ocean, they move the waters in the direction of the wind. And so we see a pattern of gyres or surface currents in the Earth that match the pattern, particularly of the high pressure systems that we see, the semi-permanent high pressure systems, where we see clockwise gyres in the northern hemisphere and counterclockwise gyres in the southern hemisphere, reflecting the clockwise and counterclockwise motion around high pressure systems in the different hemispheres. We also see the effect of upwelling associated with winds over water. If I look at the Peru current, where the waters are traveling north along the coast of Peru, as the wind blows northward over that water, the waters are deflected to the left by the Coriolis force away from the coast, and therefore water comes up from below to replace that surface water in what we call upwelling. And this is critical for the fisheries off the coast of Peru. A similar effect occurs off the coast of California in the California current. But this is the effect where we bring nutrients up to the surface and feed very productive fisheries in regions of the Earth where you get this upwelling along the coast because of the combination of the direction of the wind flow and the Coriolis force coming together. In Peru, this is associated with the El Nino, where this pattern would fail every few years around Christmas time and result in the collapse of the fisheries. And so the El Nino effect was not discovered by scientists studying meteorology. The El Nino effect was an effect understood by Peruvians in terms of failure of the fisheries with change in weather systems. And this question of the El Nino, these patterns in the circulation, leads us to a discussion of oscillations and teleconnections in the Earth's circulation system. If I look in the upper panel, I have what's called the El Nino index. The El Nino index is based on air temperature, sea surface temperature, sea level pressure, cloudiness, wind direction, and wind speed in the Pacific. And we have an El Nino condition when the index is positive, and we have the reverse condition, La Nina, when the wind condition is negative. The book does a very good discussion of how the El Nino gets set up. I won't repeat that here. I'll just highlight that the El Nino varies in an unpredictable way, but in clumps over 5 or 10 or 20-year periods at a time. That we have dominant periods for maybe 20 years of El Nino, and then we have several years in a row of La Nina conditions. There are similar behaviors in the pattern of weather in the Pacific, the North Pacific, the Pacific Decadal Oscillation. This oscillation, also as an index from positive to negative, gives dominant weather patterns. The change in the 1970s from negative to positive is associated with a change in weather conditions in Alaska due to a change in where the Aleutian low tends to sit in the Gulf of Alaska relative to the Alaska mainland. It's worth noting that the Pacific Decadal Oscillation was also discovered around fisheries, that it was people studying salmon returns in Washington that led to a deeper study of the climate that led to the idea of that there was an oscillation effect that could be described with an index that would give an insight into the patterns of weather and the patterns of salmon returns in the North Pacific. The question of why we have variations decade to decade or 5 years to 5 years in these indexes and the state of the atmosphere is an active area of research. It's not fundamentally understood except to say that different processes in the Earth atmosphere system are responding at different timescales. Heat is moving through the ocean at different timescales than it moves through the atmosphere, and so there are 10-year processes, 5-year processes, 30-year processes, and 1-year processes all mixing together that result in these patterns where we see behavior changing decade by decade. The connections of the El Nino around the world have been well documented, and here we show that when we have the El Nino warm pool off the coast of Peru in the winter, say from November to March 1997, 1998, we have a pattern of changes in weather around the world. For us in Alaska, we tend to get warmer winters in El Nino years. In the American Southwest, they tend to get wetter winters in El Nino years, warmer winters in eastern Canada, drier weather in Indonesia and Australia, and drier weather in South America and in eastern Africa. And so there are connections all around the world from these large systems like El Nino, and what forecasters try and do in forecasting what the winter is going to be like, doing a seasonal forecast, is look at the conditions, see if it's likely for an El Nino to form, and if so, then use that to guide them in what kind of winter they might expect in Alaska. Closing thoughts and summary for the unit. The first thing to take away is that the large-scale pattern of how the atmosphere moves, the circulation of the atmosphere, can be explained using fundamental principles that we've examined this semester. Our understanding of how winds arise, the geostrophic winds, how the rotation of the Earth fits into pressure gradients. Pressure gradients arise from differences in temperature. All those mechanisms that work together give rise to the pattern that we see in the global circulation, and that the 3-cell model that we've looked at in this unit gives you an 80% accurate big picture of how the weather and climate patterns of the Earth are formed. I want to highlight the idea of the movement of circulation patterns in the seasons is critical to life on Earth, particularly if we look at something like the monsoon, where the monsoon rains are critical for agriculture in India. The jet streams that form at the polar front are critical in giving us the stormy weather that we see in the North Pacific that we experience in Alaska and the Aleutians. the fact that the ocean and atmosphere are coupled and that the atmospheric circulation drives a surface circulation in the ocean, and that varies also with season. And so the major ocean currents move north and south with season, and this is a huge issue in both trade, from earliest times about where you could go if you were following the winds in a sailboat, but it's also an issue about fisheries and upwelling in the ocean and the failure and success of fisheries under different weather conditions. The study of the global circulation also leads us to the idea that there are linkages globally around the world, that El Nino years cause effects all around the world, not just locally in the Pacific. And finally, the discussion of the circulation and study of the circulation highlights that there are fluctuations in the system over 10, 20, and 30-year periods that are not completely understood as to why exactly they occur, why any given fluctuation occurs, but we understand it as that there are different time scales in the atmosphere and ocean in terms of movement of energy and heat and the circulation that gets set up.